The class of open containers, namely containers without a cover, is an important class of objects in our daily life. In this work, we proposed a novel method for robots to imagine open containability of a previously unseen object via physical simulations. For example, consider the case where a robot wants to determine the open containability of an object in the real world. The robot imagines if liquid or granular material can be poured into the object and robustly retained therein. In this work, we focus on exploring open containability for granular material. Here, we show the pipeline of our method with an origami cup and a roll of tape. Given a previously unseen object, the robot first scans and reconstructs the 3D model of the object. Then, the robot uses the 3D model to perform open containability, which simulates dropping particles from above the object and quantifies the open containability of the object. This quantification is used to classify whether the object is an open container or not. For an open container, the robot proceeds to pouring imagination to find the pouring pose for autonomous pouring. Finally, the robot pours at the imagined pouring pose. In this paper, M&M's candies are used as the pouring material. Here, we show the details of our method with a wooden bowl. The robot moves to 24 predefined poses to capture depth images for reconstruction of the object 3D model. In open containability imagination, the robot simulates dropping particles from above the object and checks if the particles can be retained therein under small perturbations. Small perturbations are introduced by rotating the object and adding horizontal force fields. Note that adding a horizontal force field is equivalent to translating the object with an acceleration towards the negative direction of the force field. Here we show the snapshot at the end of the open containability imagination. The ratio between the number of particles retained in the object and the total number of particles being dropped defines the open containability of the object. If the open containability is larger than some thresholds, the object is classified as an open container. Here, we show the initial positions of the particles before the drop. The red highlighted particles are those which end up retained in the object after the drop. The XY coordinates of these particles define what we call the footprint of the object. If the object is classified as an open container, the robot proceeds to pouring imagination. In pouring imagination, the robot simulates pouring from different positions and orientations. The particle in object ratio of each pouring is recorded for selecting the pouring position and orientation for real robot autonomous pouring. After the pouring imagination, the robot pours candies into the object from a cup at the imagined pouring position and orientation. There is no spillage during pouring into this object. Here we show more examples of open containability imagination. Here we show more examples of pouring imagination. Here are the autonomous pouring demos of the objects shown in the pouring imagination. The only pouring failure case among the 55 open containers in the test data is a vase with a small opening. The opening is reconstructed as a dent due to limitations under 3D scanning. For more details, please see our paper and visit the project page.